The invention of the steam engine in the early 1800s gave rise to the greatest enterprise on the planet. From clouds of steam and billowing smoke emerged the golden age of railroads and railway marvels. There it sat, a strange-looking device that could travel from place to place by its own power. But how? Its weight was not calculated in pounds, but tons. It was enormous. Its wheels would sink into the dirt and mud-filled roads of the day. Horse-drawn wagons were already using rails to haul freight. Rails would be the way to use the heavy steam engine. A road of rails. A system of iron rails secured to a path of wooden ties that the train could move along with its flanged wheels. Now, to get to point A from point B, all one had to do was lay down track between the two designated spots. Travel was going to be made easy. It was a grand idea, and it sounded simple.
Well, the world doesn't work that way. And generally, the shortest distance between 2 points is not the straightest or the levelest. So the railroad civil engineers have had to invest a tremendous amount of creativity and talent in figuring ways of crossing rivers and chasms, getting through or around mountains, and doing this in an economical way. So railroad marvels are really the product of creative efforts necessary to get a railroad from point A to point B.
For a time, formidable mountain ranges confined the early progress of railroads in the U.S. The mountains were great geographical barriers that had to be overcome. At first, the railroads in America were short-line. They served the ports of the eastern seacoast by delivering commerce to seaboard states. Many feats of engineering wonderment occurred all along the short lines. But the great triumph of the age was celebrated when a golden spike was driven into a polished tie at Promontory, Utah on May 10, 1869.
The completion of the Transcontinental Railroad was probably this nation's first significant railroad marvel that is easily recognizable by the public today. Before we joined East and West Coast by rail, we spoke of travel across country in months, and suddenly we had reduced the transit time to just days. And the impacts that that would have on society and how the nation was further settled and further solidified is a wonderful and very powerful story.
The Civil War had almost destroyed the concept of one united nation, but the Union survived. The North and South were once again joined. The Transcontinental Railroad bound up the wounded nation from east to west and tied it together with a ribbon of iron from sea to shining sea. The accomplishment was breathtaking. The Central Pacific Railroad had moved out of Sacramento toward the east, and the Union Pacific from Missouri. They raced toward each other in a cacophony of anvil choruses as the spikes were driven into the rails, all driven with sledgehammers and muscles of steel. More individual and extraordinary feats of engineering and construction took place in the building of the Transcontinental Railroad than at any other time in railroad history. It was a marvel and gave birth to all the marvels that would follow, as railroading became the biggest business in the world.
To think that from the 1830s, when it was a novelty, when railroading was a novelty, to just leap forward 30 years in time when it was running 2,000, 3,000 miles across a continent is quite a leap in technology.
After the completion of the Transcontinental, technology kept right on leaping. The miles of railroad track kept on spreading across the country. The peak year was 1916, when there were approximately 254,000 miles of track in the United States. And one civil engineer figured for every mile of track, there was a bridge of some sort that had been built to allow the train to find the easiest way. This included bridges of every type: wooden and steel trestle, beam, truss, suspension, soaring concrete arch viaducts, and stone arch viaducts, which resemble the ancient Roman aqueducts.
The early stone bridges were built by people who were more artists than engineers. They were using classical forms that came down from Roman times. There was no method for calculating stresses in the material. They just built and proportioned on the basis of hundreds of years of experience, which, as it turns out, has stood the test of time very well.
The stone arch bridges stand today as functioning symbols from the golden age of railroads. But they were expensive and took years to build, stone by cut stone. So engineers began to build with wood and iron.
The original stone bridges of the very early railroads are mostly still around and still in service. The bridges that followed them of wood or iron are long since gone, replaced several times over.
Near Harrisburg, Pennsylvania, both wood and iron bridges crossed the Susquehanna River at one time, before designers took a giant step backwards in time and created the graceful stone arch structure known as the Rockville Bridge.
This is the Rockville Bridge. It was completed in 1902. It's the longest stone arch railroad bridge in the world. It's the third bridge on the site. The first one was wooden, built in 1849. The second one was iron, built in 1877. But then as trains got bigger, heavier, and faster, something more substantial was needed, and so this stone bridge was built in 1902.
An arched bridge was a crowning achievement of the ancient world and is impressive even today. Like the ancient structures, the Stone Arch Railroad Bridge was, for the most part, built by hand.
The bridge consists of 48 arches. It's about 3,800 feet long and assembled from thousands and thousands of blocks of stone that were cut intricately to fit together like a jigsaw puzzle. The people who did this were true artisans of their day, the turn of the century, 1900, 1902, and the fact that they were able to make it all fit together without ever seeing the bridge is a remarkable testament to their abilities.
In 1902, noted railroad author Frank Spearman wrote of the Rockville, "Bridges like men have their tables of mortality, but here is a structure to which no limit of years may be assigned. It has been built to last forever. It is still in use today, a symbol of railroad artistry and ingenuity." Other arch bridges which grace the railroads date back to near the beginning of the 19th century. Many that are in use today will continue to be used in the future. The one-arch Carrollton Viaduct, completed in 1829, is the oldest in the U.S., and the 8-arch Thomas Viaduct, completed in 1835, is next. Despite their age, they remain a part of contemporary railroading.
The Thomas Viaduct, which is just west of Baltimore, which is a series of stone arches on a curve that was completed in 1835 for the branch of the Baltimore and Ohio Railroad to Washington, and that bridge carries 2 tracks, and it's still in service today.
The most impressive of all arch-style bridges rises up from the floor of the valley near the little town of Nicholson, Pennsylvania. It rises up to a startling height of 240 feet and dwarfs the town at its base. It was dedicated on Saturday, November the 6th, 1915. Novelist Theodore Dreiser called the viaduct one of the true wonders of the world.
Tunkhannock Viaduct up in Nicholson, Pennsylvania, built in the early part of this century in an effort by the Delaware, Lackawanna, and Western Railway to speed up its operation. Just a magnificent reinforced concrete structure that's truly marvelous and awesome just to see it rise above the valley below.
The Tunkhannock began construction in May of 1912. It is a reinforced concrete arch bridge, 2,300 feet in length. It carries 2 tracks supported by 10 180-foot double arches. Each of the arch ribs is 14 feet wide and 8 feet thick at the crown.
Thousands and thousands of cubic yards of concrete were used to build it. It took 3 years to put it up. There was so much concrete in it. And they built a big aerial tramway with big wooden towers that carried the concrete out to wherever it was needed to build the bridge.
It looms up like some lost and gigantic piece of sculpture, strangely out of place in the tranquil landscape that surrounds it. It is rarely used today. It stands there as a sentinel, a railroad marvel from an era gone by. Since prehistoric times, man has had a fascination with digging in the ground. Early cave dwellers cut little tunnels to connect their various tribal caves into a community of sorts. With the expansion of the railroads, starting in the early 1800s, man began tunneling in earnest. If a mountain stood in the way of the railroad, then by God they would dig and chip and blast their way through it. No challenge seemed too big for the early railway pioneers.
The development of all railroad tunnels is a significant story, from the Hoosick Tunnel that was developed in Massachusetts to the development of Moffat Tunnel, this 4-mile tunnel outside of Denver that was absolutely critical to our crossing the Western Continental Divide in an efficient manner.
The construction of the Hoosick Tunnel in Massachusetts was a marvel of monumental proportions. Work began in 1851 and went on until 1873. The tunnel was almost 5 miles long and ran under the Berkshire Mountain Range. When completed, it was the longest tunnel in the world. It cost $22 million when it was built and almost bankrupted the state. Its ventilation shaft rises up over 1,000 feet through the middle of the mountain. Passing mostly through solid rock, it took longer to dig than any other tunnel in history. 241 months, 22 years.
These fellows just went to work chipping away at the rock using hand tools, star drills that were manually punched into the rock, and a little bit of black powder. Then came the introduction of nitroglycerin around 1855. It was a much more efficient blasting compound than had been black powder. It was also much more dangerous to handle, and many more lives were lost.
196 lives were lost during the construction of the Hoosick. Mostly the men were blown to bits by the highly volatile and unstable explosive, nitroglycerin. In spite of this, work continued and the East met the West in almost perfect alignment. Just an offset of 7/16 of an inch in the fall of 1873. The Hoosick, in use today, attests to the tenacity of the workers and the engineering genius of the railroad designers of the 19th century. In the early years of the 20th century, the Moffat Tunnel near Denver, Colorado was built. It was made possible by drilling techniques that became state-of-the-art and are in use to this day. The tunnel was conceived by David Halliday Moffat Jr., a railroad pioneer and businessman. he was determined to connect the city of Denver with a transcontinental line. Early in 1902, at the age of 63, David Moffett announced his intention to build a railroad over the roof of the continent. He called it the Denver Northwestern and Pacific. It connected Denver with Salt Lake City. It became known as the Moffett Road, with its route through scenic Rollins Pass. But during the winter months, Rollins Pass was frequently closed for weeks at a time because of blizzards. The railroad was not showing a profit. A tunnel would be the answer. A tunnel that would allow the trains to escape the snow of Rollins Pass and become profitable. David Moffett died on March 18, 1911. But his dream of a tunnel through the Continental Divide would not die with him.
Moffett had this dream of a tunnel, which was not built until long after his death. It was finally built by the Moffett Tunnel Commission, drilled through the Rockies west of Denver, completed about 1928, as I recall, and was, I think, briefly the longest tunnel in North America. It was an extremely interesting, difficult project.
The green light for the construction of the tunnel was given in June of 1923. Camps were set up at the east and west portals and digging began. Unlike the Hoosac Tunnel that caused the deaths of so many men, the Moffett Tunnel was, for the most part, considered a model of railroad building safety. There was a strong sense of community, and during the 5 years of construction, life in both portal camps was good. So was the pay. The average worker earned $5.15 for an 8-hour shift, a high salary for that time. The mess halls were open 24 hours a day, and food was abundant, which kept worker morale high. Entire families lived at the sites. Babies were born here too. The first baby born at East Portal was named Thelma. Her father was one of the tunnel workmen. New life was welcome, but death made its presence felt also. On July 30th, 1926, a serious accident occurred in the West Portal. 125 tons of rock fell from the roof, killing 6 men. 28 men in all would die during its construction, but in railroading, this was considered a good record. A new drill was developed here that would become state-of-the-art. Called the Lewis Traveling Cantilever Girder, it allowed the project to continue after geological conditions halted work in the West Portal. The girder was a mechanism that excavated the top of the tunnel and then supported the roof as the bore was increased under it. On February the 12th, 1927, after almost 4 years, the West Portal workers broke through to the east. Celebrations followed. The tunnel was officially dedicated on February 26, 1928. David Moffett's dream of putting Denver on the main line was to be fulfilled. Finally, the Denver and Rio Grande was the line. The trains found momentary sanctuary during the winter months in the Rocky Mountains. The tunnel was, for a time, the longest in the United States at 6.21 miles. It had taken 48 months to bore and cost $15,600,000. It conquered the unconquerable, the Continental Divide. It was driven by the vision of one man, David H. Moffett.
He was truly a visionary, and he had the ability to convince people that his ideas were correct and would work. The Moffett Tunnel is the latter-day marvel and one of the latest bits of railroad construction that was undertaken in the early part of the 20th century that was critically needed. The traffic volumes by 1920 were such east and west that there were bottlenecks being created trying to get across the Continental Divide, and the Moffett Tunnel just expedited that whole process.
During World War II, As many as 30 passenger freight and troop trains passed through the Moffat in a single day. Since 1983, Amtrak's famous California Zephyr has used the Moffat Tunnel on its run from Chicago to San Francisco. A tunnel was one way to tame a mountain, but sometimes you just had to climb over it. For the railroad, the best path between point A and point B had always been a straight line with a gradient of no more than 2%. The railroad engineers went to extraordinary extremes attempting to accomplish this. Sometimes it was easy, often it was not. The Sierra Nevada was formidable, but conquerable. Donner Pass, 105 miles through the Sierra Nevada. The name, Sierra Nevada, means literally snow-covered mountains. The crossing of Donner Pass, located as close to the top of America as one can get, is a true railroad marvel of the early part of the last century. Central Pacific's brilliant young engineer, Theodore D. Judah, found the best way through the seemingly impenetrable granite peaks of the ominous mountain range. The chosen path over the mountains for the Central Pacific to join with the Union Pacific was staggering. From Sacramento, California, it climbed up through Donner Pass for 81 miles from the base and to an altitude of 7,000 feet. It was the best route. With only a few alterations, it is still in use today. The Central Pacific employed thousands of Chinese immigrant workers who were called upon to perform back-breaking and often dangerous tasks of labor.
There were many fatalities in building the Transcontinental Railroad. Around a place called Cape Horn, the mountains were so severe that the only way they were able to build the line was to lower the Chinese laborers over the side of the cliff to cut holes into the mountain and place the powder to blast and make a shelf to put the tracks on.
Some say the expression, "He doesn't stand a Chinaman's chance in hell," evolved from the horrendous experiences endured by the hard-working laborers as they cut and blasted their way through Donner Pass.
The lore, the romance of the building of the Pacific Railroad says that thousands of workers were killed in premature explosions or swept away by the winter snows in the Sierra Nevada. There are actual authenticated records indicating that as many as 500 people were killed over the 6-year construction period of the railroad. And in fact, the number may be somewhat higher, but there were not the thousands and thousands of killed that popular romantic literature would have you believe. "40 miles of snow sheds were conceived and then constructed to keep the rail lines open. They were a remarkable solution which gave the railroad assurance of year-round operation."
We could consider the snow sheds to be one of the railroad marvels of this country. Certainly when they were constructed 100 years ago, there was a great amount of vision that went into to their engineering. And the way that they were constructed to deflect the snow from the mountains, yet provided enough ventilation with locomotives could move through them without choking crew and passengers, is indeed a marvel.
The eastern seaboard had its share of difficulties as well. The desire to surmount the formidable Allegheny mountain range, which ran north and south across the state of Pennsylvania, gave birth to the first and most unusual railroad in America, the Allegheny Portage Railroad, a marvel of engineering for its time. The system was built to connect the two canal waterways on either side of the Alleghenies, at Hollidaysburg in the east and Johnstown in the west. In the strictest sense, it was not a railroad. It was a series of 10 inclined planes that gave portage to the canal boats, passengers and all, by pulling them with rope on flat cars with fixed steam engines over the mountain range to the waterway on the other side. The canal boats were designed to separate into two. Each half was pulled from the water and secured to a flatbed railroad car for the trip up the plain. On the other side, the canal boats were hooked together and continued on their way. It was breathtaking technology at its most advanced and terrifying, a marvel of engineering ingenuity.
There's wonderful stories of the Allegheny Portage Railroad and how frightened people were to get on this contraption, this contrivance, and be pulled up a mountain, and that many people, in fact, elected to walk alongside. They just didn't trust, perhaps, the technology or the construction of it, and sometimes they accurately didn't trust it because the ropes would break or something would fail and otherwise cause a disaster.
When the hemp rope imported from Russia snapped on occasion, it caused terrifying and sometimes fatal plunges to the bottom of the inclined plane. Assurance was needed, also a better rope. John Augustus Roebling had the answer. He developed a steel wire cable that was gratefully used by the Allegheny Portage Railroad and later used in the construction of his Niagara Falls Suspension Bridge and the Brooklyn Bridge. With the new cable, the trips up and down the inclined planes became safer, but the Allegheny Portage Railroad and the canals, after only 23 years, were moving toward the final years of their existence. They were too slow. By the middle of the 19th century, speed was the name of the game. The Baltimore and Ohio Railroad already reached from Baltimore to Cumberland, Maryland. The B&O was seeking approval for a route to Pittsburgh. Philadelphia feared that the Baltimore-Pittsburgh route would imperil its status as a first-class port city. The legislature rejected the B&O by one vote and granted a route to the newly formed Pennsylvania Railroad, a dynasty in the making. The Portage Railroad was considered outmoded by this time. The Pennsylvania Railroad badly needed a marvel that would allow its trains to climb the grades of the Allegheny mountain range to reach Pittsburgh, the gateway to the Golden West. A marvel was on the way. It would become known as the eighth wonder of the railroad world, a feat of engineering that took a mountain range by surprise. It scaled its heights by first turning its back and going in the opposite direction. It was to become known throughout the world as the Great Horseshoe Curve, the best train watching spot then, now, and forever. I'm taking this railroad over the Alleghenies. So said J. Edgar Thompson, chief civil engineer and president of the Pennsylvania Railroad. He proved to be a man of his word.
And Thompson, in a very bold move, elected to take the railroad directly west out of Altoona into a valley and cut off the face of a mountain using the rock spoils to fill in two ravines, created a huge semicircular arc that enabled him to gain elevation very gradually. The challenge to railroads has always been to keep gradients as low as possible. Thompson was driven by the need to keep the grade below 2%, and that translates into 2 feet of rise in elevation per 100 feet of travel.
Thompson's solution was simple and elegant. He curved his track in a graceful arc around the valley of lush forests and lakes until they just about returned to where they had begun. Just about, but not quite.
The Horseshoe Curve was a great engineering marvel when it was completed in 1854. And part of that intrigue is the fact that it's so simple. The idea was to get elevation, to climb up the mountain, and previously they had done it with hoisting trains up inclined planes. But the simplicity of this design was that they simply took the track and lengthened it by going out around, adding mileage to the route, and therefore making the grade a little easier to take.
The horseshoe curve is about 3/4 of a mile long and laid in a continuous 8-degree arc that forms a 220-degree path. From a higher vantage point, it looks like someone has thrown a gigantic horseshoe into the side of the mountain. Business at the curve has remained brisk for 150 years and includes a scenic park for train watchers.
We often say that the Horseshoe Curve opened in February of 1854, and it hasn't had a day off since. Again, another marvel. How many transportation features in America have lasted 150 years and are still in use today? Horseshoe Curve was a way to lengthen the line and keep the gradients down below 2%, which the railroad trains of the era could support and which they can support yet today.
The curve started with a single track in 1854. By 1900, 3 more had been added. At its peak in World War II, as many as 100 trains, passenger, freight, and troop carriers used the curve every single day, year in and year out. It played a vital part in our country's railroad history. Dan Cupper writes in his book, Horseshoe Heritage, the curve has been compared to a stage in which a drama of railroading is played out. Love and tragedy, fear and joy, life and death, all are a part of its history. Generations of train conductors have announced it to generations of passengers who still crowd the coach windows to get a good view of it as the train goes around. The train watchers in this country had an enormous amount of traffic to watch. At their peak, the United States railroads had almost 240,000 miles of track, and 26,000 miles of that belonged to the Pennsylvania Railroad alone. As early as 1900, on any given day on that line, over 5,500 trains were dispatched. Now multiply that by all the other railroads and wonder, how did all those trains keep from bumping into each other? Sometimes they didn't. Early on, it became clear to the railroads that traffic control was a prerequisite, not only for the safety of the passengers, but because of the promise to deliver undamaged freight over great distances. How centralized traffic control evolved from crude hand-controlled switches to computer-driven centers of today is a continuing marvel in the history of the railroad.
Centralized traffic control, CTC, basically started as a way to put several interlockings under the control of 1 or 2 block operators in one tower. In the very beginning, they literally had towers they could stand in, and that's why towers are still a little higher than a normal building, where they could see a certain distance to the next tower, and the operator in the next tower would give them the all clear the trains by, with a high ball or a flag, or perhaps a lantern at night.
Highball it out of here. The saying comes from a train signal and not from a club car. A white ball about 1.5 feet in diameter was hoisted by chain to its high position on the tower. It meant the train had a clear way. Highball it, full speed ahead. The high ball is no longer in service, but the expression remains part of our idiom.
Train traffic control was originally handled on a manual basis, and it developed to a system where dispatchers would telegraph their orders to people who were stationed in towers along the line. Later, this manual system gave way to automatic traffic control, and today it's all done by computers, by men in darkened rooms with TV screens.
Switching and controlling traffic has come a long way from the days when the tower operators manually threw heavy switches and signals by levers called Armstrong machines.
And it was Armstrong because you had to be a big guy to move them and put your weight on it. With the development of electro-pneumatic switches, all you have is a small lever, and basically you're pushing buttons, throwing toggle switches, or a small lever that does the same thing.
When Ben Franklin flew his kite in the electrical storm and discovered that current would travel along the metal wire, unbeknownst to him, he played a role in the history of railroad marvels. Electricity became a magic key to traffic control.
Probably the vast number of Americans and the public don't understand that each rail has a low voltage current running through it, and that the train, as it enters a certain section of track, shunts across the wheels and axles that current, and that causes the change in the signals ahead and behind of a train, and the development of automatic block signals. Centralized traffic control has taken advantage of the latest computerized technologies today.
On the screen behind me, you'll see all the sections that are in green. That is how far the signals are displayed by a train dispatcher for a particular train. The dispatcher's job is to route all the trains in his area the most efficient and safe way possible. An engineer's job is to follow the routing depending on the display of the signal.
Today's train dispatcher sits behind a monitor and with a touch of a finger to the screen can alter the course of a train's destiny.
They have touch screens where they can literally change trains from one track to another, display signals, stop trains if they need to. They're also in communication via radio with the engineer and other personnel on the ground, signal maintainers, maintenance of way people. They can talk directly to the train dispatcher.
Working in conjunction with traffic control is the Center for Amtrak National Operations that handles everything else that makes a railroad function. It is tied together by satellite. It too is a marvel of modern-day technology assisting the railroad to run with efficiency and safety.
The main function of the Ops Center is to tie in all of our internal, external customers together in the best way we can possibly do it. There are several hundred trains at one time running. We can have a passenger board a train in Los Angeles, have that passenger go through multiple scenic routes, end up in Chicago, transfer to a train through to Washington, and then reboard a train to New York, and we can track that passenger the entire time.
The image of a passenger who, due to poor scheduling, has missed his train, sitting in some forgotten and dark train depot, is a nostalgic image that belongs to the railroad's past. Today, the Operations Center would surely come to the rescue. The highball of yesteryear now orbits the planet with its watchful eye.
What you're looking at is the screen of the United States. One of the ways we use to communicate with our trains now is GPS. It's global positioning signals. All these yellow dots represent engines throughout the country. So I was going to look for an engine, I click right on that engine, the dot, and it'll actually take the screen down to the point where you can actually read the street address where the train is. Right here. It's in North Carolina. We can send them a message. We can ask them, do you have passenger Mrs. Jones on there with you? He's approximately that's 70 miles from Washington.
Today's traveler can feel secure because there is someone who is watching over him through every leg of his journey. The track is clear ahead. Highball it all the way. The final railroad marvel of the 20th century began in the country that invented the steam locomotive 2 centuries ago, England. And the marvel is a railroad tunnel that runs under the English Channel to France for some 24 miles. It carries passengers, automobiles, trucks, and freight between the east coast of England and the west coast of France. It has been called the Channel Tunnel, the Eurotunnel, and finally, the Channel. Everyone seems pleased with that name. The actual construction time of the channel was relatively short. The combined project, a mutual effort of England and France, took only 5 years. However, the vision for it goes back for centuries.
the fact that it has taken so long to get together the forces to build it only adds to its mystique and the lore that surrounds it. I believe it was Napoleon who even thought of doing it, but it never took place because it was such a technological barrier to overcome.
French engineer Albert Mathieu Favier presented plans for a channel tunnel in 1802, and an attempt was actually begun in 1877, but abandoned because of extreme geological difficulties. The English started a similar effort in 1881 and again in 1975, but each time the work was abandoned.
The Channel Tunnel took almost 200 years to build if you look at it in a certain way, because there were proposals to try to cross the channel in one form or another from the beginning of the 19th century and the 20th century, which didn't get very far and then came to a halt. So it was not until our time that they were finally able to pull together the financing and build that enormous project.
In 1988, work finally did begin. Digging from both sides simultaneously, the route ran from portals near the Shakespeare Cliff at Folkestone in England and from Saint-Got near Calais in France.
But the technology used to develop that tunnel was very much adapted from the American experience in construction of the Moffat Tunnel, and even a little bit earlier in the construction of the Trans-Hudson tubes of the Pennsylvania Railroad under the Hudson River. The type of boring devices that were used in the channel were direct descendants of that which Moffat developed and his engineers developed for the Moffat Tunnel.
The channel is not, in the strictest sense, a tunnel. It is 3 tunnels. Each outer tube carries train traffic in one direction and is 25 feet in diameter. The smaller connecting center tube, 16 feet in diameter, is for ventilation and service, and is linked to the main tunnels by cross passages every 1,230 feet.
The Channel Tunnel was built largely with tunnel boring machines, and those have been around for a long time, but they've become very advanced in recent years. Probably the earliest tunnel boring machine was one I mentioned that was tried on the Hoosick Tunnel in Massachusetts back in the 1840s. It didn't work, but that was the first time somebody got the idea of a machine that would bore a hole into a mountain or under a body of water, as in the case of the channel.
During those construction years, it was difficult to notice by looking at the surface of the channel that work was in progress, but indeed it was. Huge boring machines, conveyor trains, and hundreds of highly skilled workmen were down there digging a tunnel that at mid-channel was almost 328 feet below sea level. The TBMs were the children of the Moffat, but they were operated by computer and guided by laser. Their huge cutting heads cut into the chalk underground at a speed of 6 inches a minute. Following behind the TBM came the huge conveyor train to carry away the waste. Ultimately, the waste would be moved to the surface and used as fill. The historic breakthrough that connected France with England for the first time since the Ice Age occurred on the 1st of December in 1990 in the Service Tunnel. The North and South main tunnels were finished by June of 1991. The lining, track, and electrification was completed, and the channel was ready for shuttle traffic in 1994. The final price tag, $15 billion. The channel traffic is managed with a state-of-the-art centralized control command center. Safety is built in. In 1994, Queen Elizabeth and President Mitterrand traveled on the shuttle train from Calais, France, under the Channel to Folkestone, England. Ceremonies followed to officially open the channel.
Clearly, the channel is the marvel that brings us into the new millennium and will again bring with it profound changes to to the United Kingdom and all of Europe, where now you're able to leave London and a few hours later be in Paris without having left a very comfortable seat in a passenger train that moves at high speed.
Today, passengers use the Channel with assurance. They travel at speeds between 90 to 180 miles an hour as they move back and forth between England and mainland Europe. One wonders what the passengers of the 1830s who walked with terror alongside the canal boats of the Portage Railroad inclined planes would think of contemporary marvels such as the Channel. But the early visionaries of the railroads built better than they could have ever known. Their great achievements still stand today as monuments to their genius. Out of clouds of steam and billowing smoke, the railroads continue their journey from the glory of the past to the promise of the 21st century and the marvels yet to come.